So today we will be covering how to use the Kd.app apparent calculator in my MetaboMG project. So this function uses a database of metabolite binding data that comes with the package to calculate apparent KDs at any ionic strength or pH. And the application is estimating metabolite chelated magnesium concentrations in cells to add relevance, some in vivo relevance to your in vitro experimental data. So the first thing you're going to want to do is set up your computer like I have here. So I've opened, cloned my MetaboMG ITC repository from GitHub, and I've opened the project from that folder. And I have another video up on my GitHub page that you can watch to learn how to do this. The next thing I'm going to do is open up an R script and define what we need to get up to. So the first thing is we're going to set up our computer or our script. The next thing is we're going to use the KD apparent calculator, just one at a time, and I'll go over kind of some of the quirks and things you got to deal with. The next thing is we'll use the KD apparent calculator on a loop, in case you're interested in analyzing multiple metabolites. The last thing we'll do is print a little graph using base R, and then we'll also save the data as a CSV. The first thing to do to set up the script is we have to expose our functions and the underlying thermodynamics data to the memory. So we'll use dev tools load all. Okay, that'll load everything into the memory. Next thing we'll do is we'll check out the help documentation for our KD apparent calculator. And you can see it's over here to the right. You can reference it anytime you want. You just put a question mark in front of the function. And now we can actually run the function. We're going to run it for ATP. So we're going to make an object called KD ATP. That's going to be equal to the function KD app calculator. And the metabolite is ATP. Let's use pH equals 8. And an ionic strength equals 0.1 molar. Okay, and there it ran. We'll just really quickly go through what's happening here. So it calculated the KD for two different ligand binding states. The first is the ATP state where the ligand L is not protonated. It's totally deprotonated, and this is going to be prevalent at high pH. For example, for all the ATP, this one will occupy 96% of all the ATP in the solution. And then, of course, you get an apparent millimolar KD for that state. And this says Na because the protonated state of ATP is not expected to bind significantly to magnesium. So you might be wondering what other metabolites in the database, or there's no function that allows you to search, or if you were, for example, to type lowercase ATP, this would not work because it has to match the characters of things that are in the database exactly. So in order to kind of get around this, You might want to check what things are available in the database. So just to do that real quick, we're going to read in the data. So all the data is contained in this repository. I just used list files to check our working directory. And you can see here, the binding constant and metabolite concentration data is housed here. Okay. And it's this file right here. So I'm going to go read.csv this. I'm going to copy and paste one more time. And then I'm going to go ahead and run this path to read it in. Then once it's read in, I can go unique, df $metabolite, and this will give me a list of all possible metabolites. So if I want to run the Kd.app calculator on L-glutamic acid, I'd run Kd.app.calc, L-glutamic acid, pH equals 8, I equals 0.1. And I would get an apparent Kd for both the protonated and the deprotonated protonation states of glutamate. And of course, this one is going to be the relevant one because 98% of glutamate is in this state at pH 8. So up next, you might want to be able to run this on a loop. So in order to do that, the first thing we need to do is make some data to run this on. So here I have a CSV. It's open in Excel, but it's just a comma separated value text file of example metabolites in E. coli. And so here are the cellular concentrations. Here are the metabolites. And I want to read that in. So once again, we'll go list.files to find it. And again, it's right here. And so we'll make a data frame is equal to read.csv. Once again, I'm being very careful. So for example, df $metabolites. These metabolite names match the database names exactly down to the punctuation capitalization, and that's very important. So to run it on a loop, I'm going to go for I in 1, 2 length df metabolites. So this is the portion of the data frame that contains the metabolite names. So this will do repeat a thing that we're about to type here for every I in this vector. So if we run this vector, we get numbers 1 through 11, which is how many metabolites we want to do. So before that we run the for loop, I'm going to write Kd. I'm going to make a vector called Kd, which is completely empty. And then now we can use the for loop to fill it. We're going to want to do this for every metabolite. I will do it at a pH of 8 and an ionic strength of 0.1. Okay? And there it ran 11 times in a loop very rapidly. We can check our results by running Kd in the console. You can see these are all the Kds it calculated. And then we can add this to the data frame. So data frame $Kd is equal to Kd. And then if we go ahead, data frame, in order to look at the data frame, we will see we have a new column in our little table next to metabolite concentration, and now we have Kd. Okay, An intermediate step is you might be wondering how to quickly calculate metabolite chelated magnesium concentrations. So calculate metabolite chelated magnesium, or MCM. And that's really easy to do pretty quickly. So we'll make an object called MCM for metabolite chelated magnesium. And this formula is up on my GitHub page and in our biochemistry perspective. But basically how we calculate this is it's the metabolite concentration. So DF $ concentration times in millimolar times the free magnesium concentration. And we're going to make the free magnesium concentration equal to 2 millimolar, which is an in vivo relevant concentration. It ranges from about 0.5 to 3 millimolar in most cells. And then that's going to be divided by the Kd plus the free magnesium concentration. Okay? And now we have a vector of metabolite chelated magnesium concentrations for each metabolite. We can add that to the data frame by typing df $MCM equals MCM. And we can check our data frame head df. We now have another column called MCM with a series of metabolite chelated magnesium concentrations for each metabolite. Up next, we're going to try to print a little graph using base R. You can use any program, but I'll just make a bar plot with base R. So the height of each, bar is going to be df $ metabolite chelated magnesium concentration. The names of each bar will be the metabolite. And then we'll add some formatting functions. This first one, last, is to make the x-axis values turn sideways. Sex names, CX names. We'll make the values, the x-axis values a little smaller. Then we want our y-axis to be labeled MCM in millimolar. Okay, and we can run that. Oh, I misspelled something. I said names.arg. And here we get a nice little graph of each metabolite. So you can see that L-glutamic acid is chelating a lot of magnesium, ATP, UTP, GTP, and deoxythymidine triphosphate are all chelating a lot of magnesium, but the other amino acids don't seem to be chelating much. Okay. And then finally, we'll save this data frame. So df. Right here, we want to save this as a comma separated value file, which you can open in Excel or any graphing program you want. Make a table out of it, so you can go write.csv df. We'll call this example.csv. We'll call it example final.csv. And then I like to add the argument row names equals false, which will keep R from printing a column that will open up in Excel, which are these integers, the row names. And then that's it. We can check our working directory. We have our final example. It's going to open here in a sec, and yep, we've got our KDs that we just calculated rather quickly, and we have our metabolite chelated magnesium concentrations. And again, you have to take these with a grain of salt, but it's a good way to understand what the cellular condition might be.